Okay, for our first question, there is no snow on Janet's driveway when the snow begins to fall at midnight. So that means that there is initially no snow. From midnight to 9 a.m. means that t equals 0 is midnight and t equals 9 is 9 a.m. It says show accumulates, and what we really mean by that is snow accumulates on the driveway at a rate modeled by f of t equals 7t e to the cosine t. Since this is a calculator question, I'm going to use my calculator and put f of t into my y1. Okay, so notice it says that f of t is cubic feet per hour, and it is a rate. So we're actually starting with the rate n. So I have a rate n. And g of t in cubic feet per hour is also a rate, but it is the rate out. Okay, so the first part of this is how many cubic feet of snow have accumulated on the driveway by 6 a.m. Well, up until 6 a.m., no one is removing snow. So we're not removing snow at all. So that means we're just adding snow. Technically, it is the initial value plus the amount of snow that is added, which is the integral of the rate from 0 to 6. I do not have to copy the 7t e to the cosine. Since the function is already named f, we could just use f of t. Save some time, and we don't risk making a copy error. Now, the first part, you're not really graded on the plus 0 simply because it's 0. So you could put that or not include it. Now, for my calculator, I'm going to integrate, which is the fourth one down on my list, from 0 to 6, the y1. Okay, I'm going to double check. This question does not ask me to round off anything differently, so I have to keep 3 decimal places of precision. So 142.275, and it's the how many cubic feet of snow. So we end up with just cubic feet. It's no longer a rate because we anti-derived. The next part says find the rate of change of volume of the snow on the driveway at 8 a.m. Okay, so now we have to be careful on this part that we actually use the part of the g function that includes time 8. So from here, we want to make sure that we're using the 108. And now the rate of change of volume is actually the rate n minus the rate out. So it's the overall rate. So at time 8, that's actually f of 8 minus g of 8, which is f of 8 minus 108. You have to choose appropriately. And then you need to use your calculator. So f is actually what we stored into our y1. So it's just y1 of 8 minus 108. So negative 59.582. Okay, now this is still finding a rate. So since we have the rate, it's still cubic feet per hour. The next part says let h of t represent the total amount of snow in cubic feet that Janet has removed. Most people make a mistake on this because they say let h of t represent the total amount of snow, and they stop reading. That we're only doing the part that's been removed, not the part that's there the whole time. Okay, so not the amount that's on the driveway. So that means that we have to anti-derive g of t. So on here, what you have to think of is that when you anti-derive g of t, the antiderivative of 0 dt is just 0 plus c, and we're going to use the interval for that from 0 to 6. And since the initial value, the amount that's been removed at time 0, is 0, we can use that to get that c has to be 0. So initially, h of t, the amount that's been removed for the entire interval, from 0 to 6 is still no snow. Okay, now when we antiderive the next part, the 125, we get 125t plus, I'll call it d. And we have to know that at time 6, at 6 a.m., she still has not removed any snow yet, because up until time 0 to time 6, she still isn't removing anything. So we're going to use that. So if we do 125 times 6 plus d, has to equal 0. So d has to be negative, and since it's a calculator question, 125 times 6, negative 750. So that means h of t is 125t minus 750 from 6 less than or equal to t less than 7. I'm using the exact same interval notation that was used above, and you should as well. Okay, so the next part says that I antiderive 108 with respect to time, get 108t plus, we've already used f, we've already used h, we've already used g, I don't know, p sounds good. Okay, now we have to use the previous equation that says at time 7, because we're starting this one at time 7. So 7 less than or equal to t less than or equal to 9. So we need to know what was the initial value at time 7. So at time 7, into the previous equation, we should know that h of 7 is 125. And that makes sense as well, even if you kind of messed up the first equation here, because you're only removing snow for 1 hour at 125 cubic feet per hour. So for 1 hour, you've removed 125. So if we set this equation equal to 125 at time 7, so I'll do 108 times 7 plus p has to equal 125. Then we get p has to equal 125 minus 108 times 7. So negative 631. So the last part of this is 108t, a little space, minus 631 from time 7 to time 9. So the piecewise equation is h of t. This is one of the hardest things they ask you to do, the piecewise equations, because you're dealing with so many different plus c's. You know, the last part is actually what most people try to do for part C. How many cubic feet of snow are on the driveway at 9 a.m.? Okay, so really what we're doing is we're saying that the initial value is no snow. We're adding for the entire 9-hour period f of t dt. But now we're removing from time 6 to time 7, 125 dt, and we're removing from time 7 to time 9, 108 dt. So if you were unable to get the actual piecewise equations for part C, you don't actually need the piecewise equation to do this part. Initial value plus the amount in over the time interval that we're adding minus the amount out for each time interval that those apply. So I could do that on my calculator all the way across. I don't even have to do it by hand. So I'm going to antiderive from 0 to 9 the function that we stored into y1, which is f, minus the integral from 6 to 7, 125, minus the integral from 7 to 9, 108. Now what's extremely important on here is that you have to write the integrals with the correct limits on your paper. So either you had to do that for part C and have the right values, or you had to do that value here. So now that means the answer is 26.335. It does not tell me to round differently, so it has to be 3 decimal places, cubic feet of snow. Okay, this next part's also a calculator question. So I'm going to put that R, the rate that they're giving me, into my Y1. here. And since they're doing 0 to 31, I'm going to change my window on the calculator and zoom 0. Okay, so this is actually the overall rate. You see the 0 going across because I might want to find zeros later. That gives you an idea of when we're gaining, losing, and then gaining mosquitoes. Okay, notice there are initially 1,000 mosquitoes, and this is the rate in mosquitoes per day. It says show that the number of mosquitoes is increasing at time t equals 6. So we're going to do increasing means the rate, which really just means r of t is greater than 0, and specifically r of 6 is greater than 0. Okay, show that the number of mosquitoes is increasing at time 6. So we're supposed to show that at time 6, r of 6 is positive. We cannot use the graph sketch for that. We actually have to get the value. But r is the y1 that we typed in. So we can just do y1. I'll clear this out. Of 6. Put that down here. Now, it is not telling us to round differently. So that means that we have to keep 3 decimal places of precision. So we would say r of 6 is equal to 4.438, still measured in mosquitoes per day. Okay, don't use m because that's meters, so use something slightly different. And so therefore, at t equals 6, mosquitoes are increasing, so the function is increasing because, r of 6 is greater than 0. Go. Okay, the next part says at time t equals 6, the number of mosquitoes is increasing at an increasing rate, or increasing at a decreasing rate. Okay, so tricky part about this, people get confused. We already know the number of mosquitoes is increasing because of part A. The question is the rate increasing or decreasing? So what we want to know is whether r prime, the slope of the rate, is positive or negative. So we need to do r prime of 6. So with my calculator, I'm going to do the derivative of y1 at 6. Okay, so now think about this as whether or not we are speeding up or slowing down. So we're going forward faster or slower. Okay, so r prime of 6 is negative 1.913. So therefore, since r of 6 is greater than 0, but r prime of 6 is less than 0, the mosquito at t equals 6, comma, mosquitoes is increasing at a decreasing rate. Okay. So we have a positive rate, but the rate itself is decreasing. According to the model, how many mosquitoes will be on the island at time 31? Okay, nearest whole number this time. That only applies when it reads that in the particular question. So it's the initial number of mosquitoes plus the change of mosquitoes, which is the integral of the rate from time 0 to time 31. Okay, again, I don't have to copy the function down, just the name of the function, and then the dt. So it's 1,000 plus the integral from 0 to 31 of y1. Oops, go. Didn't quite work. Of y1 dx. You do have to write down the 1,000 in front of the integral because it's initial value plus change. The integral does have to have the correct limits, and it has to have the correct notation closed off with the dt. In terms of this function, do not write f of x or dx or y1 or anything like that. It has to be the function that's in our word problem. Okay, so to the nearest whole number, there are 964 mosquitoes. Okay, the next part asks what is the maximum number of mosquitoes from time 0 to 31. That's asking for the ABS max, which means we need the time, the number of mosquitoes at time 0, at time 31, and we have to get our critical numbers. So the initial number of mosquitoes is 1,000, and we actually already know that the ending number of mosquitoes is 964. So now if we look at the graph that I drug over initially, or you can look back at your calculator, you'll notice that we have a rate here. We have 2 critical numbers. Okay, so we're going to find those critical numbers. So I put into my graph the rate and the 0 because I think it's faster to intersect than to find zeros. So I'm going to calculate the intersection. Now this is somewhere between time 6, where we had a positive, and I don't know, halfway across, so let's say time 10 or 15. So 0, so between time 0, so we're going to calculate the intersection. First curve, second curve, somewhere between, let's say, time 6 and time 15. And we don't want to guess, so we're going to press enter. And didn't quite go through. Enter, enter. Okay, so let's do close to time 10. Okay, so we found our first intersection. So 7.853 or 7.854. Now what I'm not going to do is I am not going to round this off in the middle of the problem. Since we're rounding at the end, I'm going to press X and notice it has that value. So I'm just going to do this previous integral that I already did and go back and change the 31. So I'm going to delete 31, delete the 3, delete the 1, and put X in there. So we're going to go from time 0 to time X that we already have stored. And we get 1039.356. So to the nearest whole number again, we get 1039. I'm going to find the next intersection. Calculate number 5, enter, enter. And if 15 is right in the middle, I'm going to guess 20. And press enter. And so 23.56 is my next intersection. 23.562. And if I quit, notice that my X is stored again, the new X. So I can actually go and grab this one. And since it knows the new value for X, it'll use that new value for X itself. So it's a time saver. And we don't double rounds in our problem. And so the next value is 842.404. So to the nearest whole number, 842. Okay, so we found our zeros on our calculator. This part we're not actually writing down. We have a table of values that is always going to include, for absolute maximum, the endpoints and the critical numbers. So this is actually the analysis that leads to our conclusion. And then we actually have to state the conclusion. What is the maximum number of mosquitoes? Okay, so at t equal to 7.854 days, 1039 mosquitoes is the absolute max. Okay. That's it. We always do ABS max and min with critical numbers and endpoints. Critical numbers can come from zeros or undefined spots of the derivative. Okay, so the next problem is the dreaded cone problem. This container has the shape of an open right circular cone. We would be given the formula for the cone. They are giving me the diameter, however, so we have to adjust as the radius is only 5 centimeters. And so we have the proportion that R over H is equal to 5 over 10, or 1/2. So R equals 1/2 H, or vice versa, 2R could equal H. It says find the volume V of water in the container when the height is 5 centimeters. So since we're only dealing with height and volume, we want to get rid of R. So I'm going to change my volume function and get rid of the R. So 1/3 pi H squared over 4 times H. So my volume formula that I'm going to use is pi over 12 h cubed. So the volume is pi over 12, 5 cubed, or 125 pi over 12. Have to use the correct units of measure, and so since we have centimeters for the height, we have centimeters cubed for the volume. The next part says find the rate of change of volume with respect to time when h is 5. So in our paragraph above, we are evaporating the water, so the height is changing at a constant rate of negative 3 over 10 because we're losing height. So they're giving us dH dt is negative 3 over 10 centimeters per hour. So we're again going to go from that same simplified volume formula, so that dV dt is pi over 12, and then 3h squared dH dt. So the change in volume over time is pi over 4, because the 3 and 12 cancel, h squared, so 5 squared is 25, and dH dt is negative 3 over 10. And you can leave this as long as you include the units centimeters cubed per hour. If we're going to simplify this out, it would be negative 15 pi over 8 centimeters cubed per hour. Now the next part says show that the rate of change of volume of the water in the container due to evaporation is directly proportional to the exposed surface area of the water. The exposed surface area is talking about just the circle on top of the water that's touching the air. So what we want to do is show that the evaporation is directly proportional to the change in volume, directly proportional to the exposed surface area of the water. Okay. We already have dV dt is equal to pi over 4 h squared dH dt from right up above. So what is this exposed surface area? Well, it's the area of that circle, pi r squared. I know that dH dt is negative 3 over 10, and I'm showing that the volume change is proportional to pi r squared. So now, since r is equal to half h, 2r is equal to h, and I can substitute that in here and put 2r in here squared. So the change in volume over time is equal to pi over 4 times 4r squared times negative 3 over 10. So the change in volume over time is pi r squared times the constant negative 3 over 10. So at any time, so the reason I didn't substitute in a specific r value or specific dV is we're not showing this at h equals 5. We're showing that the change in volume is always proportional to the surface area of the water. So we do in fact have the change in volume is equal to the surface area, pi r squared, times the constant, which is the rate of change of h. So that is exactly what directly proportional means. This is a very tricky thing to do. They're asking you to know algebra 2 proportions in addition to the calculus derivatives, and actually just how to get those to equal each other. Okay. Now this next one is asking me to do. All right, so on here, we're looking for the area of this rectangle that would actually be maximized. And so the area of a rectangle is length times width. So if this point is on the curve, let's call it xy, then the height or the length is actually y, and the width is actually 2 x's, because 1 x is only referring to this part. We're going to assume that the x is the positive part because we're talking about length. Okay, so now if we want to find this so that you have the area to be maximized, we need to maximize the area formula, which is y, negative 4x squared plus 4, times the 2x. So to avoid the product rule, I'll distribute here. So to maximize the area, I take the derivative of the area, and I'm looking for x and y, so I don't have to try to do this as a rate. We're not doing a how fast question. So negative 24x squared plus 8. I'll set that equal to 0. So 24x squared equals 8. So x squared is 8 over 24, which is 1/3. So x would be plus or minus the square root of 1/3, and since x we're referring to as a length, we're going to choose the positive square root of 3 over 3. Okay, now to prove that this is a maximum, well, x has to be larger than 0. And we're going to put the root 3 over 3 in. So if we substitute into our derivative formula to figure out whether we have an increasing or decreasing, a positive derivative or a negative derivative, if we substitute something smaller in, we're going to get a positive. If we substitute something like 10 in, we're going to get negative 2400, so that's negative. So therefore we have a max at x will be root 3 over 3, and then the y value. Well, the y value is negative 4x squared, which is 1/3, plus 4. So negative 4/3 plus 12/3, so 8/3. Okay, the next part is a related rates problem. As the point moves, the x-coordinate is changing at a rate per second. That's the rate of change with respect to time. So that's when we do the dx dt. It says find the rate of change of the area. So I'm still going to use the simplified area formula as negative 8x cubed plus 8x. But now the change in area over time is negative 24x squared dx dt plus 8 dx dt. Now the x-coordinate is increasing at a constant rate of 2, so dx dt is a positive 2 units per second. Okay, so at the rate of, find the rate of when x is a half, so we're looking for the change in area over time. When x is a half, x squared is a fourth. We already know dx is 2. Plus 8, and we already know dx is 2. So the change in area over time is negative 12 plus 16, or 4. And area is square units, and time is still in seconds.
Okay, on the next problem, we have a ladder that is 15 feet long leading against the building. So 15 feet for the ladder is actually fixed constantly. So I'm going to label that on my diagram as a constant. And for the length of OX, technically they're asking you how to link the segments OY and OX. I'm just going to put a little x and a little y, so that on here I can say to let the length from O to Y, which is expressed as similarly to a segment without the bar on top, be little y, and the length from O to X be little x. So it says find the rate of change in feet per second at which the length OY is changing when the length for little x is 9, or when the point x, which is different here, the big X is actually a point, is 9 feet from the building. So when x equals 9 feet, it tells us in the problem that the point x is being moved away from the building at a constant rate of half a foot per second. So dx dt is a positive half foot per second. So setting up the relationship that x squared plus y squared equals 15 squared, then 2x dx dt plus 2y dy dt equals 0. Now I am going to divide the 2's out of everything, and 0 divided by 2 is still 0, and substitute in. When x is 9, dx is a half, the y value we need, the dy is what we were looking for, and the whole thing is still equal to 0. So if I go back to x squared plus y squared equals 15 squared, and 9 squared plus y squared equals 15 squared, so 81 plus y squared equals 225. So y squared equals 144, and y equals 12. So I'll substitute that value in. So 12 dy dt equals negative 9 halves. So dy dt is negative 9 halves divided by 12. And technically I can just throw all here feet per second. I don't want to simplify, which again, I do not have to simplify at all. If I do simplify it, because I'm going to use the value again for part B, which makes the simplified version nicer, I can factor 3 and cancel. So that means -3/8 feet per second. The next part says find the rate of change in square feet per second of the area of the triangle XOY. Remember, the area of a triangle is 1/2 base times height. So the area for this triangle is 1/2 little x times y. And we have a product rule. So the change in area over time is equal to the derivative of the first, which is 1/2 dx dt, keep second, plus the first times the derivative of the second, which is dy dt. So the change in area over time is 1/2 times the dx, which is also a half, times the y value that we found above, which was 12, plus 1/2 the x value, and the dy, which is -3/8. So technically, I can now stop and put square feet per second. I'm going to simplify that out. The dA dt is 12 divided by 4, which is 3, minus 27 over 16, which is 48/16, minus 27/16, or 21/16 feet squared per second. So if they had asked me whether or not the area was increasing or decreasing, I really would have needed to simplify to figure that out. Otherwise, definitely stop here. Okay, the figure above shows an above-ground swimming pool in the shape of a cylinder with a radius of 12 feet and a height of 4. That means, because we're not doing an oil spill, that R equals 12 feet is actually a fixed constant. The pool contains 1,000 cubic feet at time 0, so I actually have the initial volume given to me. And during the time interval 0 to 12 hours, so that's my window, since this is a calculator question, water is being pumped in at the rate of P of T, cubic feet per hour. So this is the rate M, cubic feet per hour. But water is leaking out of the pool at a rate R of T, cubic feet per hour. So that makes the R of T the rate out. The first part says to use a midpoint rerun sum with the 3 sub-intervals of equal length to approximate the total amount of water pumped in. We don't care how much was already there. So this does not include the 1,000. It only includes what was pumped in between time 0 and time 12. Show the computation. You absolutely have to write the integral for what you're doing. So from 0 to 12, we are anti-deriving P of T dt. So cubic feet per hour times hours. We can approximate that using a Riemann. It tells us to do the midpoint. So I'm doing every other value, and it tells me the fixed delta x. So that's going to be 4. So I can factor out the 4 and do 46 plus 57 plus 62 in cubic feet, because we found out the total amount of water that was pumped in. Okay, now since this is a calculator question, you will need to simplify that out. Plus, you're going to use that value later in this particular problem. So 660 cubic feet. The next part says to calculate the total amount of water that leaks out. This still does not include the 1,000 that was already there. Just what's leaking between time 0 to 12. So that's 0 to 12 R of T dt. Notice for this that I'm not trying to recopy this R function down. I don't want to make a copy error and lose a point, so I'm just writing the R of T version. So I'm going to go to my calculator, type in 25 e to the negative 0.05x I want my window to be 0 to 12. And if I want to see what's happening, I could zoom 0 to see what kind of rate I have when I'm losing. So we're losing a lot of water. Okay, so now I just want to use my calculator to an anti-derived from 0 to 12. The function that I just typed into y1, dx. So 225.594. This does not tell me to round off at all, either for part A or for part B. So I cannot round. So it's 225.594 cubic feet. So the amount of water that we've done. Now, part C says to use the results for part A and B to approximate the volume of the water in the pool at time 12. Round your answers to the nearest cubic foot. That means regular rounding, not round up because you want to or round down because you're trying to justify why you think that's correct. Nearest cubic foot, regular rounding. That does not mean anything else is rounded. This is the only part that asks us to round. So now this part does include the initial value. It's how much was in the tank initially, or in the pool initially, plus the amount that we pumped in, minus the amount that was removed. And we are going to round afterwards, not in the middle of the problem. Do not round off to the end of the problem. Minus that previous value, 474.405. Okay, so 474.405. So that means it's approximately 474 cubic feet are remaining at 12 hours. So we're losing much more than we're gaining, depending upon how much time passes by. Okay, so find the rate at which the volume of the water is increasing at time t equals 8 hours. How fast is the water level rising? Find the rate of the volume at time 8. Okay, so they're actually giving us that information. The change in volume over time at t equals 8, or v prime of 8, is actually the rate in minus the rate out. That's your overall change in volume. So the change in volume at time 8 is actually the part pumped in, the rate in at time 8, minus the rate out at time 8. The pumped in at 8 is in our table of values, is 60 cubic feet per hour. Is that labor hours? Yes. Minus R of 8, which I need to get on my calculator. So I'm going to do 60 minus. R is just the Y value for Y1 at time 8. So that's still the rate. So 43.242 cubic feet per hour. The next part says how fast is the water level rising. That's actually asking us for DHDT. So we are told, but we won't be on the test, that the volume of a cylinder is pi r squared h. For us, since the pool has a fixed radius, it's 144 pi h. I'm lost. I'm going to be that way just for my function. There we go. Accidentally deleted my page. Okay. So the change in volume with respect to time is the constant 144 pi times dHdt. Well, at time 8, we just found the ddt. So 43.242 dot 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 dot. I don't want to use a rounded value. Equals 144 pi dHdt. So dHdt is going to be the previous value that we found, not rounded off, divided by 144 pi. Now on your calculator, that means you're going to have to put the fraction in, the previous value, divided by 144 pi, or you would have to put the previous value, the old calculator, divided by parentheses 144 pi. Otherwise, you're only dividing by pi and dividing by 144 multiplied by pi, which would be wrong. Okay, so we should have gotten 0.0955. So 0.096. It is height over time, which means feet per hour. So there are two answers to that part, indicating units of measure, which we did. Okay, so the last free response, and then we'll record a new video for multiple choice, says, a particle moves along the x-axis, so its velocity is given by the function. The particle has a position of 8 at time 0. So that really means x of 0 equals 8. Find the acceleration. It's a calculator allowed question, so I'm going to put velocity into my y1. So we'll do that now. I'm going to clear everything else out. We have the natural log of t squared, or x squared, minus 3x plus 3. So now it asks us first to find the acceleration at time 4. The acceleration at time 4 is the derivative of velocity at time 4. So I'm going to have the calculator do this derivative because you do not know how to do this derivative yet. So the derivative of the y1 function at time 4. So the derivative of velocity at time 4. And we got 0.714. No units because they did not give us units. The next part says find all the times at which the particle changes direction and during which time interval 0 to 5 does the particle travel to the left. So make sure that you're setting your interval for your window. I went to y equals and put a 0 in here because I want to find zeros. And then I'm going to zoom 0 to fit the window to the interval 0 to 5. So I have two intersections here. This is 1, 2, 3, 4, 5. So it looks like they're at 1 and 2, but we want to double check. So I'm going to intersect. So that's the reason I put y2 equal to 0, so I can intersect. So enter, enter, enter. And x does equal 2. And if I calculate the next one, number 5, I intersect, enter, enter. I don't want to find the same one again, so I'm going to say, well, I know it's close to 1. Let's see if that's correct. And it is. So it actually intersects at 1. Okay, so now I have intersection at x equals 1 and an intersection at x equals 2. So my velocity number line, and remember the velocity is the y1 function y values, not the slope. The slope of this one is acceleration. So from time 0 to time 5, I have a positive velocity, and then a 0 at t equals 1. Then I have a negative velocity, then a 0 velocity at t equals 2, and a positive velocity again. So find all the times at which the particle changes direction. So I would, since they're asking me more than one question here, I need to label my answers. So the particle changes direction. At t equals 1 and 2, because velocity changes sign. Not because something goes below an x-axis, which is not even true because this is a v and t graph. No x. Okay, now the next part says during which time intervals does a particle travel left? And so I would say the particle travels left on the interval 1 to 2 because velocity is less than 0. The last part asks us to find the position of the particle at time 2. So that means the initial position at time 0, which is 8, plus the change in position from time 0 to time 2, which is the integral velocity. You must write this out. You do not copy the natural log. You use v of t as your notation. You use the calculator. So it's 8 plus math for the integral from 0 to 2. Of the velocity function that's stored in y1 dx. So 8.368, in this case, 8.369, either way, round or truncate. Okay, the last part says to find the average speed. Speed is the absolute value of velocity. To average that, we are going to do velocity times time divided by time. So we're doing speed times time divided by time. Speed times time divided by time is going to give us the average speed. Okay, this is the notation exactly as it should be on the paper. You don't have to copy anything else down. Please make sure your absolute values are in the correct place. They should not be outside the integral. It has to be the integral of speed. The speed has to be on the inside. And then we're going to do the integral from 0 to 2. The absolute value, which is here under your F2, along with your derivatives and integrals, of the y1 function that's already stored, which was velocity. So now we have the absolute value of velocity, speed, being integrated over time, and then dividing by time. So this should be how it reads on your calculator, and you get 0.371. And still don't make up units, please. Okay, so that's the last of our free responses, so we're going to pause, go to lunch, come back.